Hello everyone, this is Professor Lee again. We are going to continue to investigate probability in chapter 3, right? So today's topic is chapter 3.2, independent and mutually exclusive event. Now, as I always said, the topic of each chapter is very important, right? Because it tells you exactly what we are going to study and cover. So we are going to cover the concept of independent and mutually exclusive event, right? All right, so before we get into the actual independent and mutually exclusive, let's talk about conditional probability again, right? Conditional probability. Remember that conditional probability that we used to, we studied in last chapter a little bit. It's probability of A given B, right? So that symbol right here, that we read this as given. So this really means we are looking for probability of event A, right? We are looking for probability of event A, but we have a condition. What's the condition? B has to happen first, right? That's what this conditional probability is trying to say. We are looking for probability of A, but we have a condition. What's the condition? B has to happen first. Or should we say we are looking for probability of A within B, right? Within B. So look at this Venn diagram here. You know, this graph right here, this is a Venn diagram. So, you know, the whole box, the big box right here, that's a bad line, but anyway, they say this is S. Now, can someone, guess what this S is going to be? This S refers to sample space. So what's sample space? It's a collection of every possible outcome, right? It's a collection of every possible outcome. So S include every possible case. Now we have this A case and B case, and we call this A and B as an event. So we have event A and event B. Now, when we say A and B, look at this right here, A and B, that means it should be in A at the same time it should be in B. And this is the notation right there. See that? A, right here, A and B. So that right here is and, right there. So where is A and B then? It has to be in A and it has to be in B at the same time. See that area in the middle? That's A and B area right there, right? That area right there in the middle is going to be A and B. What about A or B? A or B is right here, and this is how we write it. I mean, sometimes they do write A or B, but in mathematical notation, you do A. It's almost like a U, right? Or B, like that. And that right here is or, right? That's or. Okay, so where is A or B? A or B means it could be in A and it could be in B. So it includes everything in here, right? It includes everything. Everything in here. So A or B means it could be in A and it could be in B, right? All right. So, we talked about this conditional probability. Now, be careful with the order of this A and B. This is we are looking for probability of B now, not A, B, but we have a condition. What's the condition? A has to happen first. So how do we actually rewrite this conditional probability with A or and the probability of A? Well, just like this. Just like this. So what goes under? The given part goes under. And the top part is just going to be whatever that we have here and here. And so probability of B given A is going to be probability of A and B over probability of A. Now, let me ask you this. Do you think order here, probability of A and B, and probability of B and A, do you think these are different or these are the same thing? These are the same thing, right? Probability of A and B and A, that's right in the middle anyway, right? This part right here, right? So in case of and or, the order doesn't really matter here, right? So let's say if you're looking for probability of A given B, what do you think this formula is going to look like? Now take a look at this formula. Take your time. Let me give you a little bit of time. Try to write this formula and we'll verify it together. I'll try to write it together, you know. Why don't you try it right now? Right? Why don't you try it right now? So you'll get your pen. Look at this given formula right here. See which one goes under and what do we have to write on the top, right? And try to write this formula right there. Because this one given right here, this is probability of B given A. What we are trying to figure out here is probability of A given B. So let me give you a little bit of time. So what goes under? The given part goes under. So this is going to be what? Probability of B goes under like that. And what do we write on the top? Probability of A and B, just like that. Now, what about probability of B and A? Well, that's the same thing, right? Doesn't really matter, right? So you can write B and A if you want to, but doesn't really matter. You know, A and B, B and A over probability of B. That's it. That's the formula right there. That's the formula for what? What's called conditional probability, right? Okay. So probability of, let's talk about this. Probability of B given A, as you can see, the given part goes under and top part is just probability of A and B. Now, from this formula, we can actually rewrite this formula in a slightly different way. What we are trying to do here, let's try to multiply. Let's try to multiply probability of A on both sides. Probability of A on both sides. I mean, can we do that? Can we multiply? Think about it. What's the probability of A at the end? What's that going to be? The probability of A at the end is just going to be a number. So it's okay to multiply a same number on both sides, right? In an equation like this. It's okay to multiply the same number on both sides. So if you multiply A on both sides, then what will happen? See that? And that cancels out. Why? Because technically that probability of A is probability of A over 1. And this is on the top. This is on the bottom. If we have same term, the top and bottom, then we can cancel it. So I can rewrite this as probability of A times probability of B given A, I'm just rewriting this part right here, equal, now what? This probability of A and B, just like that, right? And of course, if you switch this side, if you write this one in here and write this one in here, and that's the formula that we have right here. That's the formula that we have right here. All right, so I mean, let's go back a little bit. What are we doing here, right? What are we trying to do? What's going on here? What's going on here is this. We start from the concept of probability, conditional probability, and we figured out that conditional probability, that we can rewrite it like this. This is a conditional probability formula. But from the conditional probability formula, in a way, we figured out this formula for this probability. Now, what is this symbol? Do you remember what this is and how do we read this? Is this A, what? A and B. This is and. So we just figured out the formula for conditional probability, but we also figured out formula for and probability of A and B, right? Using conditional probability. But as you can see, these are not two different formulas. Basically, these are the same formula, put it in a slightly different form. So let me take a 30-second break. You think about this, right? And try to figure out what's going on here, right? Because sometimes it takes time to digest these things. So we start from the conditional probability and we rewrite the conditional probability formula in a slightly different way. So we came up with another formula, but it's the same formula, but it's another form that we have and probability in the left-hand side. That's what's going on. I mean, if you're still a little bit confused, that's okay, because we didn't do any solid example yet, right? But as you can guess, I'm sure that we will do a solid example later. Okay. So now let's introduce the concept of independent event, right? Let's introduce the concept of independent event. So two events A and B are independent if knowledge that one occurred does not affect the chance of other occurs, whatever that means. It means like something like this. Let's say you have event A and event B. They don't interfere with each other. That's independent. Let's say you are a very independent person. What does that mean? You are on your own. You don't get affected by others, right? That's what it means, right? Independent. You're a very independent person. That means you don't really, get tickled by the surrounding or anyone else. You can stand on your own. That's being independent. Very similar concept here, right? Independent in probability means when you are looking for probability of A or probability of B, you don't have to consider what's happening in the other side, because these two events, they don't interfere with each other. They don't interfere with each other. Then that's independent event, right? Now, if they are independent event, meaning if they don't interfere with each other, Look at this right here. This is telling us this. This is telling us how to figure out this probability. What is this? This is probability of A and B, as you can see. How do you actually calculate probability of A and B? Well, in case there's two events, meaning event A and event B, if they are independent, all you need to do is simple multiplication between these two events because they don't interfere with each other, right? However, if these two events are not independent, sometimes they say not independent, sometimes they say dependent, right? So sometimes they say not independent, sometimes they say dependent, same thing. If they are not independent, what does that mean? That means they interfere with each other, right? What happens in A matters when you consider what happens in B, because they are affecting each other. That's not independent. And as you can, I don't have to write it here, it's right here, right? That means it's a dependent. But sometimes you just say it's not independent, right? So if they are dependent, then what? Again, look at this formula right here. When you try to figure out probability of A and B, you cannot simply multiply these two probability like independent case. You have to multiply probability of A times probability of B given A, right? Because if they are dependent, meaning they are interfering with each other. So when you consider the probability of the second part, B, you have to consider that A has to happen first. Now, have we seen this formula before? Well, you bet we did. Right here, right? The previous page, right here. Isn't that the formula right here? So wait a minute. So are you saying that we have two separate formulas for AND, one for the independent case, just like that, and one for the dependent case, like that, and conditional probability, assuming that these two events are dependent? Yes, you are correct, right? Conditional probability. Look at the conditional probability formula right here. I mean, think about it. The name itself, the term is conditional probability, meaning what? These two events A and B, they are affecting each other. That's why we need to consider the condition, whether A has to happen first or B has to happen first. If they don't interfere with each other, there's no point of considering conditional probability because they are on their own, right? Okay, so just to remember this, we have two separate formulas for figuring out probability of, let's say, A and B. For independent case, this is our formula. For dependent case, this is our formula. And that's for probability of A and B case. Okay. Now, so how would I know these two events? Let's say we have this event A. Let's say we have this event A and event B. How would I know these two are dependent or independent? Well, sometimes it's very clear because the question itself is going to state that these two events are dependent or independent. sometimes it's not clear. Sometimes we have to figure on our own. However, there are some keyword that we can actually figure it out, whether these two events are dependent or independent. Whenever that you read the question, if they say with replacement somewhere in the question, that means these two events are independent events. With replacement, let's say when you are picking something, when you're picking a marble, when you're picking a card, right? And once you pick the card, when you put it back, that's what they mean by replacement, right? When you pick the card and put it back, that means whatever that you picked in your previous try, it's not going to affect my current try. Think about it, because it restored the original condition, right? Let me give a quick example. Let's say we have 2 red marbles and 1 blue marble right here, right? And I am picking 2 marbles now, and I want the probability of picking red and I mean blue and red. But so first one has to be the blue, second one has to be the red. So what's the probability that my first one is going to be the blue marble? Well, I have 1 blue marble out of 3 blue marble, right? So this probability is going to be, probability of blue marble must be 1/3, right? What about the second marble to be the red one? Well, I have 2 red marble, but what do I do with the first marble that I picked? Do I put it back or do I keep it? Because it matters. If you keep the first blue marble that I picked, that means now I only have 2 red marbles and both of them are red. So the chance for me to pick this red marble is just going to be 2 out of 2, 100%, 1. But if I do not put the first, if I do put the first marble back, that means with replacement, that means you put it back. If I put the first marble back, now then probability of getting the red marble is going to be, I have 2 red marble out of 3 altogether. So, the second probability is going to change. And that's the concept of replacement. So if you put it back, then it restored the original condition. So it doesn't matter what I picked in my first try. My second pick, it's got nothing to do with my first pick, right? That's independent, right? You think about it, right? That's independent. However, let's say without replacement, that means you are keeping your first pick. Then, of course, when I'm picking my second ball, I like to know what I picked in my first try, because it's going to change my probability of picking my second ball, right? If that's the case, what I pick in my first one matters, and it affects when I'm picking my second ball. That's independent. That's a dependent, right? Because it matters. And whenever that the question says without replacement, that automatically means these two events are dependent event, or you can say not independent event, right? Not independent event. Okay. So just to remember, whenever that you read, when in the question it says independent, I mean with replacement, that means these two events are independent events. Whenever that you read without replacement, that means these are dependent events. Well, yeah, okay, I kind of get it. So you're saying that whenever that I read replacement, that's independent event, and whenever I read without replacement, that means it's dependent. So dependent event. So what? What's then what? I don't really get it. What? Well, independent event, then what? What's the big deal? Well, if it's an independent event, what would be the answer for probability of A and B? Answer for this would be probability of A times probability of B. Simple multiplication. So question will ask, oh, find the probability of A and B, and they explain the situation. And in the situation, they'll say with replacement, and find the probability of A and B. What do? Well, you just simply multiply these two probability. But in the question, you know, the situation is like that you're picking two balls without replacement. Find the probability of A and B. That means what? That's a dependent event. So what do? You have to use probability of A times probability of what? No. Probability of, yes. B given A. You have to use this formula. I mean, oh, professor, where did you get this formula? Well, I got it from here. Right, remember the previous page? If it's an independent, then whenever that we ask and question, we simply multiply these two. Whenever it's a dependent, when they ask for and question, you do this conditional probability. Right? Okay, again, we take a 15-second break. Right, so with replacement, independent means just multiply these two. Without replacement means dependent, so you need to consider the conditional probability formula. Okay. All right. So let's talk about this playing card. Now, have you guys seen this card? Have you played this card? If you played this card, you must be very relatively old. The kids these days, they don't play cards, right? They play you know, video game. They you know, with the cell phone, mobile app games and all that, right? When I was in college, there was no cell phone. Cell phone was not invented yet. So we used to play card. You know, go to like a school cafeteria, like a bunch of people, you know, they play cards. I guess still they still do, right? They still do. Anyway, just in case that you do not know what the ordinary deck of playing card looks like, it looks like this. Right? So they don't have number one, they have this ace, right? The ace. And they have four different shapes, right? Four different suit. They have club, spade, heart, diamond. And the numbers actually ranging from 2 to 10, and with also, you know, ace. And they have 3 royalty. This is jack, queen, and king. And as you can see, we have 2 black cards and 2 red cards, right? So, you know, we have, if you consider ace as 1, you have 10 cards here, and you have 3 more. So each suit has 13 cards. So 13 times 4, we have 52 altogether, right? 52 altogether. Let me ask you this. If you have to pick one card out of this deck of cards, what's the probability that it's going to be spade ace? What's the probability that it's going to be spade ace? Well, which one is the spade ace? Right here. You only have one card out of 52 deck of cards. So, you know, probability of getting, you know, spade ace, let's say this event as spade ace, then, you know, I mean, how did you know this is ace? You know, I just made it up. It does, you can make up your own event. You can call it event 1 if you want to. You can call it whatever you want, right? So spade ace is going to be 1 out of 52, just like that. All right, let me ask you another question. What would be the probability if I pick one card? It's going to be any ace card. It's going to be just ace card. I'm going to call that probability of just getting ace. I have 1, 2, 3, 4 ace out of total 52 cards. So it must be 4 out of 52, right? Because I have, you know, 4 ace out of total 52 cards. If I just pick one card, then it's gotta be 4 out of 52, just like that. And you can see why, you know, this card is, and probability, you know, it's kind of it goes well. I mean, you know, if you go to casino and play this card game, it's all about probability, right? It's all about probability. You know what? And casino is always a losing game, right? They're not like, you know, charity that they don't want to give you money. They want your money, right? So think about it. If you go to casino, then you're gonna lose, right? Because, you know, they want your money. They you know, they carefully calculate the probability so that, you know, they can pay rent and, you know, build more buildings, or, you know, pay their employees. And so, you know, don't go to casino, right? Just saying. Anyway, let's talk about this example. A fair and well shuffled deck of 52 cards. You're supposed to pick how many cards? 2 cards. So, you know, if this is my real example, then I'll definitely circle those important words. And 2 cards, then I'm going to circle it. 2 cards with what? With replacement. Now, with replacement, what was it? Is it dependent or independent? With replacement. With replacement, independent, right? With replacement, independent. So we know that these 2 cases are independent cases. What's the probability that it's going to be 2 queen? 2 queen means what? Probability of getting queen and queen, right? That's what they mean by 2 queens. Now, these 2 are what? Is it independent or dependent? It says with replacement, that means it's a independent. Right, independent. So if these are independent, then how do you calculate this AND problem? Let me go back. If it's independent, AND problem is simply multiplying these two probabilities together. Right? Multiplying these two probabilities together. So this would be probability of the first one, queen, times the probability the second one is also queen. Now let me ask you this. What would be the, if you pick one card from this deck of cards, what's the probability that's going to be a queen? Now how many queens do we have here? We have 1, 2, 3, 4. So this must be 4 out of 52 times. What about second one? How many queens left? Not 3. We still have 4. Why? Because we put it back with replacement. That means you put the first card back. So we still have 4 queens out of 52. Just like that. So with replacement refers to these independent event. If it's an independent event, I mean this is just first queen and the second queen. That means these are just simple multiplication. And if it's simple multiplication, we just simply multiply these two, and you got this. You know, how do you calculate this? You multiply the top together, and you multiply the bottom together like that. You know, which is like this. And then if you reduce it, it goes something like this. Okay. Some of you might have a question about this calculation. So, you know, 4 out of 52, you know, I'm just considering one of these. This is the same thing as 4 times 1 and 4 times 13. So even these two, 4 cancels out. So this I can rewrite as 1 out of 13 times 1 out of 13. And 1 times 1 is just 1. 13 times 13, 169. Just like that. You can do it like this. And later on, I'm going to show you a very nice trick with the calculator. Then you can actually, you know, this calculator these days, they actually do this, these reducing to the, you know, simplest form. They do it for us sometimes, you know. So I'll show you later, you know, how to work with this calculator to do this. Okay. Now, this is another question. Look at this question right here. It says, without replacement. Let me go back. Without replacement means what? Without replacement means these are dependent events. If these are dependent events, we are going to use this formula, right? We can't just simply multiply these two. We need to consider this, given that A happened, right? So let's try this. So without replacement, that means it's going to be dependent event. If it's a dependent event, this AND question, you do probability of the first one times probability of the second one, but given that the first one has to happen first. So, I mean, this one is what? This one is just picking one card, and that card is going to be a queen from this deck. So we know that we have 1, 2, 3, 4 queen out of 52 queen. So it's just going to be, this one is just going to be 4 out of 52. But let's consider this one right here. What does it say? It's saying something like, I want the probability the second card is going to be queen. But I have a condition. What's the condition? First, that card that we pick and we're not putting it back, that card must be a, what does it say? The first card must be a queen. So let's say one of those queens that we picked and we are holding on to it. How many queen left? 3 queen left. Out of how many cards? Now it's not 52 anymore because I'm holding on to one of those queens. Now I have 51 cards left, just like that, right? So there you go, just like this, right? So again, this, you know, we can reduce it. This one is 1 out of 13. I guess this one we can reduce it as what? 1 out of 17, I think, right? Yes. So you can rewrite it as 1 out of 2, 2, 1, just like this. Okay. Okay. So again, later on that I'll show you, this one you just multiply these two like that, and then you reduce it like this. But you can reduce it here and got it like this. Or, you know, I'll show you a cool trick with the calculator later on to reduce this. Right? Okay. Now, let's talk about mutually exclusive. Mutually exclusive. Mutually exclusive is similar concept as independent and dependent, but they are different things. They are different things. Mutually exclusive simply means this. They cannot be both at the same time. That's a mutually exclusive, right? That's a mutually exclusive. Something like this. You know, if a, you know, can you wear jeans and not wearing jeans at the moment at the same time? No, I mean, you know, let's not talk about some of those, you know, very, you know, bizarre and, you know, extreme case. In a normal sense, you know, you either wearing jeans or you're wearing something else. So this event, wearing jeans, not wearing jeans, you cannot have this at the same time. So this event of wearing jeans, not wearing jeans, these are mutually exclusive event. When you roll a die, can you get even number and odd number at the same time when you roll a die? No. You know, you are either going to get even or odd. You cannot have both at the same time. So when you roll a die, getting even number, getting odd number, these two events are mutually exclusive event, right? Mutually exclusive event. Let's say, so probability of A and B must be equal to 0 if they are mutually exclusive. And let's try this example. Let's say you have, in sample space, you have number ranging from 1 to 10, right? And event A is 1, 2, 3, 4, 5. Event B is 4, 5, 6, 7, 8. Event C is 7, 9. So probability of, no, not the probability, event A and B, it should be in A and it should be in B, it's right here, 4 and 5 here, 4 and 5 here, just like that. Probability of A and B, which we only have 2 elements right here, is going to be 2 out of 10. Why is it 10? Because we have altogether 10. Only 2 of them, which is 4 and 5, is in A and B at the same time. And it's not equal to 0. And clearly, event A and event B are not mutually exclusive. Why? Because there's overlapping. It could be in A, it could be in B at the same time. What could be in A and B at the same time? 4 and 5. 4 is in A, 4 is in B at the same time. So if there is any element, any member that could be in A and could be in B at the same time, these are not mutually exclusive. If they are not mutually exclusive, A and B are not equal to 0. However, if they are mutually exclusive, A and B is going to be equal to 0. What about A and C in this case? A and C. Is there any overlapping between this A and C? No, there's no overlapping. That means A and C are mutually exclusive. If they are mutually exclusive, then what? Probability, it's right here, but probability of A and C must be equal to 0. Because they are mutually exclusive. Okay, so let's try this example. Flip 2 fair coins, and sample space is going to be either HH, HT, TH, TT, right? You flip once, you're going to get H or T. You flip again, you're going to get H or T here, or H or T here. So this is going to be HH case, this is HT case, TH, TT, just like that. And these are the sample space right there. And these are equally likely outcome, right? They have the same equal chance. Let's define event A as getting at most 1 tail, right? The maximum number of tails that you can have is up to 1. So that would be HH, HT, TH, right? Not TT, TT is the 2 tail. Event B as getting all tails, right? It has to be TT. So event A and event B, of course, they are mutually exclusive, but moreover, they are complement to each other, right? Because if it's not A, it must be B. If it's not B, then it must be A, right? So remember that complement, we write it like that, A prime, A complement, that's same thing as B in this case, right? So probability of A. What would be the actual probability of A? Right here. We have 3 out of 4. Because why is it 4? Because in the sample space, we have 4 of them. And in A, we have 1, 2, 3 of them, right? And probability of B is just 1. So when you add probability of A and plus probability of B, if they are complement to each other, it's got to be add up to 1. Right? It's got to be add up to 1 if they are complement to each other. Okay. It's kind of still a little confusing, but one thing that I want you to remember at the end is this formula, this boxed up formula right here. this formula right here. And this is saying if we have a probability of event A and probability of event A complement, then when you add it, it must be add up to 1. So at the end, I want you to remember this formula. Right? All right. So 2 fair coins flipped, same, sample space, and let's see the HH two head, and let B be 2 tail case. Then, of course, probability of can you get 2 tail and 2 head at the same time? Because it means at the same time, and no. So it's going to be 0, and you can see that event B and event C, they are mutually exclusive, meaning you cannot get 2 head and 2 tail at the same time, right? Okay, so same case. We have a sample space, all this equally likely. Let D be TT, 2 tail. Then probability of D that it's going to be 1/4, right? Because you have one of them out of 4. Let E be event of getting head on the first row. Implies you don't really care whether you get head or tail for the second row. So head on the first row will be what? This one you got head. This one you got head. And that's it, right? So HT, HH, that would be E. So probability of E is going to be 2/4. Or you can say 1/2, right? Find, okay, what about this next one? Find the probability of getting at least 1 tail in 2 flip. At least 1 tail. At least 1 tail case would be what? I mean, if I circle it here, this one has at least 1 tail. This one has at least 1 tail. This one has at least 1 tail. It has 2 tails. So HT, TH, TT, which is 3 out of 4. Right? We have 3 cases, just like that. All right. So that was it, right? That was a long lecture, but I hope that you are getting close and close to the better understanding of this relatively confusing topic, probability. All right. So that's the wrap for this lecture.